All right, let's get started. Welcome everyone back to 264A. This is our second lecture. And let me start with a couple of announcements first, which is your homework one is pretty much ready. We should be releasing it either later today or at most tomorrow. You'll get a notification when it is released. And let me also say that the class notes or chapters that we're distributing actually cover more material than what we will do in class. So you need to go by what we cover in the lectures as far as the scope. Sometimes they elaborate on things, again, that we will not go over. So your guide is the lecture. What we'll do today is two main things. The first thing is we will do quantified Boolean logic. We started with Boolean logic or propositional logic last time. We did the basics. We're going to add a few more elements which lead to what's known as quantified Boolean logic. And then we'll get started with our chapter 2 of the class notes. And that's the subject of resolution, which is a very fundamental notion which have many uses, as you will see. All right, so as usual, I'm going to go and now turn my camera off and go to the whiteboard so we can start with our discussion. The first thing we're going to be doing is quantified Boolean logic or propositional logic. And then the second thing is resolution. And in the discussion on quantified Boolean logic, we will find ourselves adding three things, what we call the conditioning operator, this guy, we'll see what that means. And then we'll add two ways to quantify existential quantification and universal quantification. So we will go over these, explain the formal definitions and the intuitions, and give you a hint of the uses of these guys. The discussion of resolution is more involved. It has many parts to it. And that's partly because resolution has many uses. It's basically an inference rule. And again, we'll explain what that means. And it's something that has been subjected to a lot of study, both in AI and more generally in computer science, very fundamental notion. All right, so let's start with quantification and quantified Boolean logic. And I'm gonna write it here. All right, so the first thing we're gonna start with is this notion of conditioning. Sometimes it's known as restriction. This is typically used, for example, in the double E literature when you study Boolean functions and so on. So what is that? It's pretty simple. What you have is basically, let's say, propositional sentence, delta, and then you have a particular variable, let's call it P, and then what you can do is condition delta on P, or you can condition delta on not P. And we write this way. And in this case, we write it that way. And it's pretty simple. We substitute a value for P. So in this particular case, we simply replace occurrences of P by true. And as you can imagine, in the other case, we replace occurrences of P by false. So we're basically saying we know the value of P. And go ahead and get rid of that variable and put in the corresponding value. So if this guy was, let's say, a simple clause, which is A or not B or C or not D, and then I want to go ahead and condition this guy on B, then in this case, I will get A or not true or C or not D, right? So this guy here is false, and then this simply will simplify to A or C or not D, all right? So what you can see here now, B is no longer there. I basically know its value. I'm declaring its value to be true, and I'm doing the substitution. If I go ahead and condition this guy on not B, then you will basically, I'll be replacing the occurrences of B with false. So then I will have A or not false, or C or not D. Can someone tell me what this would reduce to in this case? You can type this to the chat box. What will this simplify to in this particular case? All right, so I'm getting a whole bunch of people saying true, right? So this is true in this case, and this whole thing becomes true. This is basically conditioning. Now, it's not simply to set the value of a variable, but now you will see that it will enter into defining the other two parts of quantified Boolean logic. It's a fundamental operation. We'll see that set solvers that we will discuss next time will actually use this notion quite a bit. And just so that people are aware, anytime you have alpha or false, that's basically alpha. Anytime you have alpha or true, that's basically true. So we use these facts here in the simplifications that we did. Now, there are many different uses for conditioning. And I'm gonna start with one of them, which is quite fundamental. It does underlie, for example, the main algorithm behind SAT solvers. And let me do it here. So if we put here conditioning and restriction, this is known as Boole's expansion. And sometimes it's known as Shannon's expansion. I'm gonna write it, and maybe you guys can tell me why do you think it's important or where it could find its uses. And let me do this in blue here. So if you have a knowledge base or a sentence, delta, and let me repeat here that we use the term knowledge base and sometimes KB to typically mean a set of sentences. So you will have alpha 1, alpha 2, alpha n. And we use this interchangeably with the notion of a sentence, because we interpret this as just one big sentence, which is the conjunction of these guys, right? So I would be saying knowledge base, or I'll be saying sentence. That's basically the same. Now, let's go back to Boole's expansion or Shannon's expansion. What we have here is some knowledge base delta. You pick up any variable, and then we can rewrite this in the following way. Okay, look what happened here. In a way, I wrote it as a disjunction that has two ingredients. This ingredient here, this first part, where I went and I conditioned on P. What does that mean? I took delta and I set the value of P to true. And then I conjoined that with P. And then in the second part, I set the value of P to false in the knowledge base, and then I conjoined the result with not P. The main thing you have to realize here is if you look at this guy here and this guy here, can you state a main observation about these two components, delta given P and delta given not P? Let's see. Okay, I think I have a few answers here, but some of them are saying they don't have P in them. They have fewer variables. Absolutely. This guy does not mention P. And similarly for this guy, neither of these mention P. So if this guy had n variables, then these guys will have n minus 1 variables. And as you know, in computer science and in algorithmic work, what this basically means is I took a problem over n variables, and then I kind of reduced it to a problem over n minus 1 variables. That's basically the main thing that you need to start doing recursion. And you will see that this identity here, Boole's expansion or Shannon's expansion, is the basis of something known as the DPLL algorithm, a very famous algorithm in AI and computer science, which underlies SAT solvers. Of course, current SAT solvers go way beyond that, but we will get to this. Remember this, you need to remember this. This guy is pretty important. Let me highlight it here. I don't like green, but let's do this, Shannon's expansion. Okay, now let's go to the second and third ingredient of quantified Boolean logic, where we will end up using this particular construct. And I'm gonna have to erase this. And let me go back to black. So this is called, actually this deserves a bold title. This is called existential quantification. All right, and what happens here is we will introduce an operator, which is the existential quantification operator. So we will have there exists P delta. Okay, now delta is a knowledge base and P is a variable. And then I will say, when I write this, I'm saying I'm existentially quantifying the variable P out of delta. And the definition of this is the following. And we'll see now what it means and why is it important. So look, the subtle difference between this and the Shannon expansion or the Boole's expansion. I'm taking the knowledge base delta. I'm setting the value of P to true. That's what I'm doing here. And then I'm taking delta and setting the value of P to false. So now I'm getting two sentences. Neither of them mention P, and then I take their disjunction. All right. Now, why would you want to do this? So again, the first observation about this guy is that this expression here does not mention P. Now, in the Shannon expansion, I did something similar, but the expression that I got is equivalent to delta. This expression here is not equivalent to delta, it's something else. And now you're gonna tell me what that thing is and what it means. And let's take a concrete example and then we would try to see what this guy is in that context. So if my knowledge base delta is made up of two sentences, let's say this one. So let's make it like a set, and then B implies C. So this is what I have. This is my delta. And I'm gonna try now to existentially quantify the variable B out of this. And we will follow the definition as is, and we can be aided in that case if we go ahead and write this using clauses as a CNF. So it will end up being not A or B. This would be the first guy. And then the second guy will be not B or C. So that's another way of writing this particular delta. And what we'd like to do is compute that exists B out of delta. And as we know, this is delta given B and then delta given not B. So we'll just go ahead and do these guys. And if we do this, we simply do substitution. So I have not A or true. And then I have not true or C. And let's see, what does this simplify to? Can someone type in what would this simplify to in this particular case? So I'm getting an answer that it simplifies to C, and indeed that is correct. So let's now, because true or something is true, and this is false or C, that's C, and then C and true is just C. So if we do this guy here, and now I'm gonna get not A or false, and not false or C. And what does this simplify to in this particular case? What does this delta given not B, what does it simplify to? So that I can put the two together. Okay, and people are saying that that's not A. Excellent. Okay, so now we have there exists B delta equals effectively this or that. So C or not A. And if I want to write this as an implication, it ends up being this guy. Okay, I'm going to highlight what we started with and what we ended with. This is what we got. Okay, and this is what we started with. So I took this knowledge base, A implies B, B implies C, and I said, let me existentially quantify the variable B, and then I got that particular expression. One thing you will realize in this case, which is not accidental, that this existential quantification of B from delta, that is implied by delta. This follows from that, correct? The fact that A implies C, that actually follows. That's an implication. It's a little bit more than this. And to state that, let me just put it here and say that in general, you will get the following property. If alpha is a sentence that does not mention P, then, right? Then delta implies alpha if and only if there exists P delta implies alpha. Okay, stare at this for a second. What this is saying is, when I existentially quantify a variable P, I lost it. It's no longer mentioned in the knowledge base. So it's like I erased it from the knowledge base. So now I'm getting a new knowledge base. The question is, what good is that new knowledge base? And what this says basically, it is as good as the original knowledge base as far as answering questions that do not involve the variable P. So in this case, this particular sentence alpha does not mention P. It's free of P. And if I want to know whether it follows from delta, I can do the test by checking whether it follows from this guy. So in a sense, existentially quantifying P removes the information that I have on P, but doesn't remove any other information. Anything that does not involve P is still preserved. In the most naive way of using this, let's say you have delta has 100 variables, and then your queries only involve, let's say, 15 of these variables, right? So when you ask questions, you're gonna only ask about 15 of these. So in principle, you can go and existentially quantify the other 85 and just get a knowledge base over those 15 variables. And that would be as good as the original one as far as answering questions on your queries. There is more sophisticated uses of that, but because of this semantics or meaning, this is sometimes also known in AI as forgetting. So I would say that I'm forgetting P, right? And so instead of saying I'm existentially quantifying P, I'm forgetting P. And sometimes it's known as projecting delta on all vars but P. So forgetting P from delta, all right? So you have forgetting, projection, and existential quantification, and so on. Okay, this is existential quantification. We will find actually many uses for it later, and it's pretty fundamental. Now there is a dual notion, which I'll mention very briefly, And then this would be what we need to cover about quantified Boolean logic. So the other notion is, and this is universal quantification. And it's not as intuitive, but I'll just mention it, give the definition quickly, and the duality with existential quantification is not as intuitive as existential quantification to explain, but you can imagine what that is. So I have for all P delta, and the definition is you take delta and set P to true, and then you take delta and set P to false, and you take their conjunction. And you'll see in your chapter what is the guarantee that you get in that case on this guy. But what I want to just mention now is the duality between these guys. And that is that if you have there exists P delta, that is the same as for all P not delta. Let me write the other one, and I'll give you a simple way to see this duality. So here I'm expressing existential quantification in terms of universal quantification, and here we're doing the other way around. Basically, to see, this duality, if you remember, we'll talk actually more about this later today, is when you have a Boolean expression and you try to push the negations inside. So if you have something like this and you want to push the negation inside, this becomes not alpha or not beta. And if you have this, look what happened here. What happened, we flipped the conjunction to disjunction, and this here, we flipped the disjunction to conjunction. So you get this. And this you may have seen as De Morgan's law. Similarly, if you're doing, if you're pushing a negation through a quantifier, it flips. So look here, if I'm pushing the negation inside, I'm walking through a for all, then that becomes there exists. So let's do this here. So you basically, you push this inside, it becomes there exists, and P, and then not delta. And these guys cancel, so there exists P delta. And similarly here, if you push this inside, then you basically get for all P, it flips, and then not delta, and they cancel, and this is for all P. All right, so when you push a negation through a quantifier, that basically quantifier flips. Okay, this is all I needed to say about quantified Boolean logic. We're gonna see the uses of existential quantification later. It's pretty, fundamental, has many applications. And any questions before we move on and start talking about resolution? Okay, someone is asking, is quantified Boolean logic the same as first order logic? No, let me say a word on this. It can get confusing because, so this is quantified Boolean logic. We took Boolean logic and we added these quantifiers. And usually when you go from Boolean logic to first order logic, you also get quantifiers that exist and for all, but they're different. But let me just mention very quickly what's going on here and actually answer a question that I missed last time when I was looking at the videos very quickly. To go to first order logic, you have to introduce objects and relations between objects. So you end up having something like loves X, Y. We don't have this here. There's this notion of a relation, loves, which relates to kind of objects. So first order logic gives you first also ways to describe objects in a complex manner, and then it gives you an ability to specify a relationship between them. And then when you do that, then you can start doing quantification over objects. So you can write something for all X, there exists Y, where loves X, Y. Okay, see what's going on now? These for all and there exists there over objects. And that's a different deal. You can see how expressive that that gets. Now, let me make a couple of observations. When people started doing logic in AI, they were focused on first order logic because, as you can see, it's pretty expressive and allows you to do quite a bit of things. But due to computational complications, later there was a lot of advancement on Boolean logic. And as far as being able to do inference efficiently, and then even when people use this, they will try to use restricted versions of it that allow you to do inference by reduction to Boolean logic. So they would not apply first order inference, but they will take something like this and write out an equivalent Boolean logic knowledge base and then do inference on it. And actually that's still pretty common today. The other thing that I want to mention is someone asked last time, and I missed it. I saw that when I was, seeing the video. Says, what does first order means? What does first refer? Like, is there a second order? Yes, first order means that I can only quantify over objects, but there is even something more advanced called second order logic, where you can start doing quantification over relations. I don't know how many people are doing this today. That's pretty sophisticated and complicated. But if you look at the original papers by John McCarthy, he does make use of second order logic in some cases. Okay, I hope this explains things. And the resolution basically is what we would call an inference rule. So let me explain quickly what that is. And then we'll go into resolution. So an inference rule is something that allows you to derive sentences from a knowledge base that follow from the knowledge base. Actually, one thing that you probably know is an inference rule known as modus ponens. And this is basically, it says if you have alpha and you have alpha implies beta, then you can infer beta. This is the way we typically write it. So this means if you have a knowledge base and this knowledge base contain this and contain that, then you're free to add this to the knowledge base. It's a logical conclusion from the first two, so you can add it. And there are many of these inference rules, and resolution is one of them, which we're going to focus on right now. But as an example, if your knowledge base contained, let's say, A, and then C, and then A implies D, right? Then from this, and sometimes we would write this, I can use modus ponens to derive what? Right, look at the pattern. Think of this as alpha, think of this as alpha implies beta, then I can derive D, right? And this is called derive. Someone asked about that symbol last time. So I'm able to derive D from the following three guys using the inference rule of modus ponens. Now, resolution looks like this. Resolution says, if you have the following two sentences or patterns, if you want to think about them, then you can infer the following. All right? Look at the pattern here. I have alpha or beta, and then I have not beta or gamma. So it's like, sorry, this should be gamma. And what's happening here is like as if I'm canceling these two guys, they're canceling. And then I'm inferring alpha or gamma. If you want to think about it a little bit differently, let's try to make, use implications instead. So if I want to write this as an implication, I can write this as not alpha or beta, the first guy. And the second guy would be beta implies gamma. And then the last guy will be not alpha implies gamma. Now it makes more sense, right? I just chained these two guys together and I obtained this. But this is the standard way of writing resolution. A couple of terminology. This is called resolvent in this case, and I would say that I resolved alpha or beta with not beta or gamma. All right, so, and sometimes we would say resolved over B, over beta. Okay, we're gonna start using this terminology as we move on. Now, the one thing that you need to know about resolution and more generally about inference rules, people talk about whether an inference rule is complete. So they talk about completeness. Anytime you say, here's an inference rule, or usually a set of inference rules, people will say, are they complete? What does that mean? Complete means, are these rules sufficient to derive every possible logical implication of a knowledge base, right? We defined last time, if you have a knowledge base delta, what does it mean for something to follow from it, right? We have a definition that has nothing to do with the inference rule. It has to do with models. What are the models of delta? What are the models of alpha? So if I give you delta and alpha and I say, does alpha follow, logically follow from delta, you have a test for this. Now the question is, if indeed delta follow, if indeed alpha follows from delta, am I able to derive it using resolution? Right? Will resolution allow me to discover alpha, assuming that alpha logically follows from delta? If that's the case, that is, if this, then that, then we will say that that rule R is complete. It is able to discover everything that logically follows from a knowledge base. A question I have for you, is resolution complete? Now, this may look like a very difficult question. In general, it is difficult if I allow you to prove that a rule is complete. But sometimes if a rule is not complete, all you have to do is show a counterexample. Show me something that follows a simple knowledge base, something that follows from it, and then you tell me, well, look, I mean, there's no way that resolution can infer that. And a simple example in this case is if you have a knowledge base delta, which simply contains two things, A, comma, not B. That's all it has. A, and then not B. And let's look at alpha. A or not B. What do you think? Does alpha logically follow from delta? In this case, does alpha follow from delta? Logically, yes. So if I know A, then I know A or not B, and so on. But resolution cannot get you alpha in this case, right? Will not trigger on delta. You cannot apply resolution to this guy to obtain that particular guy. So in this case, this would be a counterexample that resolution is not complete. However, and this is where it gets interesting, resolution is complete in a particular sense, and we're gonna talk more about this in just a little bit. And this is the, it is what's called, let me erase something here. In fact, let's just start a new page. So resolution is the following. When applied to CNF, resolution is refutation complete. No, we don't need that many. Okay, let's highlight two things here. In fact, I put them in quotation, let's underline them. There's two qualifiers in this particular case. When you apply resolution to CNF, and that's typically when it's how it's used, it's being applied to conjunctive normal form, then it is refutation complete. Refutation complete means if that CNF is inconsistent, then resolution is guaranteed to discover that. So it's complete as far as detecting contradictions or inconsistencies, assuming that the knowledge base is in CNF. And we will basically get to this in just a little bit, I want to first mention a particular thing about how CNFs are normally represented in certain contexts, which facilitate doing, resolution on them and other things. So let's look at what we said CNF is. If remember, this is conjunctive normal form. Pretty important form, and it's usually a conjunction of clauses. So it would be something like A or not B, and C or D or not E, and dot, dot, dot. Now, when working with CNFs and resolution and so on, it's common to use something called clausal form, where we represent clause as a set. So in this particular case, let's just say that we only have two clauses, which are these guys, okay? Then what you would do is you represent this clause as the set A, comma, not B. And then this guy would be the set C, comma, D, comma, not D. And the whole CNF is a set. So now this is my CNF. And this is what's called as a clausal form. A clause is a set, and a CNF, so a clause is a set of literals, and a CNF is a set of clauses. Okay, I'm gonna just show you one thing that gets facilitated when you're using this notation, and then we'll take an example, a concrete example of resolution. Now you can write resolution as follows. All right, so given clauses CI and CJ, where P belongs to CI and not P belongs to CJ, resolution concludes CI. Remove that. Okay, now this looks like maybe too wordy, and why is this complication? When you're doing algorithmic work later, this set notation is actually very handy as far as expressing pseudocode and so on. But let's say CI is the set A, B, not C, and let's say CJ is basically B and C and D. And what we're going to do here is resolve over the variable C, right? So what are you going to do? You're going to remove this guy from that guy, remove this guy from that guy, and then take the union. So the resolvent in this case will be A, B, and D, right? So I took this guy, removed this from it, and I took this guy and removed this from it and took the union. Another way of looking at it, I took these two sets, removed that, and I obtained the following. Okay, let me, before I show a concrete example, this guy here should be someone's asking, this is a union, right? No, okay, you're right. You're talking about this guy here. And correct, this should be set subtraction. Very good. Thank you. Okay, let's take a concrete example of this. And here's, I'm gonna show you, because this is the style people use to do what they call resolution derivations or resolution proofs. I do have a knowledge base that have 4 clauses, and I'm gonna list them and number them. So what we have here is the following. So we'll do this and take our break. And then I'm having this guy here. Now, I want you to first take a quick look at this guy and tell me, is this a consistent or inconsistent knowledge base? And before we start applying resolution to this. So you want to think of this as a CNF that have 4 clauses, right? 1, 2, 3, 4, but when we do resolution, we list them like this and number them, and you'll see why this is useful. People are already saying this is inconsistent. One way is to look at what is this actually. This is not P or R, so this is the same as P implies R. And this is not Q or R, so this is basically Q implies R. And this is just not R. And this is P or Q. Okay, maybe now intuitively you can see why these guys are inconsistent, but for those who detected it quickly, that's pretty good. Let's go ahead and do resolution. So we have to pick two clauses and resolve them. And let me help you with the first one. We're gonna do 5 and we're gonna resolve 1 and 3. So the question I'm going to ask you, if I'm going to resolve 1 and 3, what variable am I resolving over? I'm resolving over R. So if you do that 1 and 3, you resolve this with that, and you simply get what we have here, which is this guy. And this is, by the way, we're going to get to this in a little bit. This is also called unit clause. Clauses that have a length 1 are very special. They're called unit clauses. We're going to get back to them later. Let's go ahead and say 6 here. And let's do 2 and 3. What should I get here in terms of a clause? I'm resolving 2 and 3. So I'm again resolving over R. And in that case, I should get the unit clause. So this is 2 and 3. 2 and 3, I'm resolving these two guys. I should get basically not Q. Good. And so when people type to the chat, you know, a good convention is to do this for negation. So this would be negative Q. It would be easier than trying some other symbols. Okay, let's do again. What can we do here? Perhaps any suggestions? People are saying, okay, someone said 4 and 5. So if we do 4 and 5, we cancel this with that and we get Q. And then, okay, now here's something interesting. If you look, we already derived a clause not Q. The unit clause not Q, what does it mean? Just means not Q. There's no disjunction here, not Q. And 7 says Q. So I derived Q and I derived not Q. So at this point, I already have a contradiction. But typically people finish this off by saying, I'm gonna resolve now 6 and 7. And when you resolve them, you get this, which is the empty clause. And when you have the empty clause, then that signifies a contradiction. And now basically resolution was able to establish that this knowledge base is inconsistent. Now I'm going to say a couple of words on empty clause before we leave, but let me just mention something. This ended with an empty clause. That means the knowledge base is inconsistent. It's possible that you will apply resolution to exhaustion. That means you can no longer find any more applications of resolution and you have not discovered the empty clause. In that case, you know for sure that the knowledge base is consistent. And this is the guarantee that the resolution gives you when it's applied to CNF. If there is a contradiction, it will find it. And if it runs to exhaustion without having discovered a contradiction, that means the knowledge base is consistent. Let me just mention something very quickly here. If you have a disjunction like A or B or C, an empty disjunction is false, because basically this is the identity element for disjunction. If you have a conjunction like A and not B and W, so this is empty disjunction. An empty conjunction would be true. So an empty clause is an empty disjunction, so it's falsehood. Now, having said that, in our clausal form, if I had an empty clause, that would be false. But remember, a CNF in a clausal form is a set of clauses. So what if this was empty? What if I had a clausal form that was just the empty set? It has no clauses in there. What would that represent? That would represent true. So a CNF in clausal form that is true would just be this, an empty set of clauses. All right. And an empty clause is false. Let's take our 10-minute break and then we'll come back at 11 and I'll be looking at the chat box meanwhile to see what questions I will answer when we get back.